Okay, I think we can start now. Can you hear me? Okay, so let me share my screen. Okay, can you see the screen? Okay, good. In this exercise section, we'll discuss some questions related to renormalization. So let's have a brief review of what is renormalization. So, so we all know that in calculating the amplitude, we have to include, apart from the three level diagrams, we also have to include the high order diagrams, right? Because the amplitude is something like a perturbation series. So we have to include all possible diagrams. So for example, here, if we consider electron muon scattering, we have one three level diagrams and one high order diagrams. And we can prove that the amplitude will be like this. And so this term will be correspond to this diagram, and this whole term will be corresponding to this loop diagram. And because we have a loop here, so there will be an integral over this internal momentum k. So so this is the amplitude, but the trouble is that this whole integral is divergent. So if you just pick up the leading order of the k, so this integral can be so it's something like this. If you just pick up the k, so you can see that this is divergence if we integrate k from 0 to infinity. So this is divergent, and this so this make the whole amplitude divergence, and this not physical. So people want to find a way to deal with this divergence. And first, people impose the method of regularization. That is, we replace the upper limit by so-called cutoff M, and this is the results when we impose this cutoff mass. And so you can see that now the whole amplitude can be written in two terms. One term is this log m square over m square, and this will be the problem of this divergence. And there's another term which is a function of q square. So this is what we get after imposing regularization, but this doesn't solve the problem, because at the end we'll make this m cutoff very large, and this will also make the amplitude divergence. So so let's first rewrite this amplitude into this form. So this term will be proportional to GE square, and this term will proportional to GE to the fourth order. And now the key point is that we define a new coupling constant, which is called a renormalized coupling constant. And then the whole amplitude can be rewritten into this in terms of this G out. And then we argue that so you can see that in this new amplitude, the M cutoff is absorbed into this renormalized coupling constant. And so you do not see M cutoff here. And then the key point is that we argue that it's GR that we measure in experiment instead of GE. So GE is something like unphysical, and GE is not what we measure, and it's GR that we measure in experiment. So we can argue that there may be, so the GE may have some cancellation with this N cutoff, and this will make the GR small. And that's how the people deal with these infinities. And this method is called renormalization. And we are leaving with this term, and this term is the physical correction from the high order diagram. So by renormalization, we simply absorb these infinities into the renormalized coupling constant, and then we say that this is what we measure, and we are living with this true correction from the high order diagrams. And finally, we can also absorb this Q square dependence into this running coupling constant to include the effects of the high order diagrams. And we know that the coupling constant is related to the fine structure constant like this. And so we can measure the fine structure constant to in experiment to validate the theory. And usually, and if Q square is equal to 0, so Q square equals 0, that means there's no momentum transfer. So you can imagine the two charges are very far away, so they didn't exchange any photon. And in this case, we say that the two charges are fully screened. So this will be 1/137. So that's a brief review of normalization. Any question? Okay, so let's do some exercise related to renormalization. So the first question asks us to find the energy at which the coupling constant or the fine structure constant blows up. So so here's the expressions, and if we want to find energy which alpha blows up, we can simply make the denominator to be 0. So we are arranging the terms is like this. And so we can simply get the energy to be mc squared multiplied by square root of an exponential. And then we can substitute some values. So for the m, we can simply choose electron or muons. It doesn't matter. And for alpha 0, we can substitute the experimental value 1/137. And after that, you can see that the energy is about 10 to the 281 MeV, which is absolutely not accessible by any colliders on Earth. And so experimentally, we don't have to worry about the breakdown of QED. And in this such high energy, we even don't know whether QED is still valid or not. So we don't have to worry about this. Okay, so let's do the B part. So the B part, we want to find the energy at which the alpha deviates from the alpha 0 by 1%. So we can simply set up these equations and solve for the Q square. So we are arranging the terms and substitute the expression for alpha Q square. Can get the equation like this. And similarly, we can solve the energy. So similarly, we can substitute the electron mass and also the alpha 0. And you will find that the energy is about 300 MeV. And this is absolutely accessible by colliders. And so we can test the QED and also renormalization theory in this experimentally. Okay, so let's move on to question 2. So in question 2 is related to QCD, and in QCD there are some several differences. And so the first difference is that in QCD, in the loop diagrams, we have something like the gluon loops, while in QED we only have the fermion loops. And due to these gluon loops, there will be some factor here. And here the N is the number of color in the standard model, and F is the number of flavor of quarks. And another difference is that we cannot choose alpha 0 as the reference point, because in QED we can safely separate two charges very far away and measure the charge. But in QCD we cannot separate our two free quarks. So we have to choose another reference point, and we label it as mu square. And we can combine this mu square with this vector to form a new variable lambda. And now we want to prove that using these two relations we can derive this expression. And it's quite straightforward. So we just pick equation 1 and break down this log. And we substitute equation 2. So we substitute this log mu square by log lambda square, and this 12 pi over alpha s. Yeah, and then we explain the multiplication. And then you can see that this will be 1, and this can cancel with the 1 before. Okay, so and we can combine this again, and you can see that this alpha s will cancel each other. And finally, we can combine this log. Okay, it's quite straightforward. So in question 3, we want to do some substitution. So we just make use of this expression that we derive in question 2. And we can simply just substitute. So in standard model, we have 3 colors, red, green, blue, and we have 6 flavors for quarks. And So we can just substitute several values. And experimentally, lambda C is about 100 MeV to 300 MeV in this range. And here you can also see that when the energy increase, we can see that the alpha is decreasing. So in QED, if we increase the energy, the alpha will increase. But here you can see that the alpha is decreasing. And that's why we have asymptotic freedom. Okay, is there any question? Why Q square has absolute sign? Question. Yeah, because if you go back. So here, if you consider the center of mass and you express Q in terms of the external momentum, yeah, you can try yourself. You will prove that Q square is negative, and so in order to be more convenient, we use an absolute sign in this expression. Any other question? Q square has to be negative all the times, just in some case. Actually, I'm not quite sure, but in center of mass is always negative. But I don't know whether in other frames is negative or not. Okay. Did professor return the midterm paper to you, or he mentioned any progress of your midterm? Yeah, I have asked professor, but he didn't reply me. So yeah, you can ask him in afternoon. Or grade, I don't know, because it's not graded by me, because midterm is graded by professor. And he didn't reply me about the progress. So yeah, because some students asked me about the midterm. Yeah, I don't know. Okay, if there's no question, then we can stop here. Okay, goodbye.